Welcome to Senior High School Math Series. Let us have solving logarithmic equations and inequalities under General Mathematics Quarter 1 Week A based on Curriculum Implementation and Learning Management Matrix for K-12's most essential learning competencies. Here is our learning competency: solves logarithmic equations and inequalities. Before we continue, let us ponder on this. One has to divide one's time between politics and our equations. Equations are much important to me because politics is for the present, while an equation is for eternity. This is by Albert Einstein. Okay, let us have some recall of important properties of logarithm. The logarithm of 1 to the base b is equal to 0. So the logarithm of 1 to any real number base b is 0. The logarithm of b to the base b is equal to 1. So the logarithm of a number to a base equal to that number is equal to 1, except 0. The inverse property: the logarithm of b raised to x to the base b equals x. B raised to the logarithm of x to the base b is equal to x if x is greater than 0. We have one-to-one property of logarithms. The logarithm of m to the base b is equal to logarithm of n to the base b if and only if m is equal to n. Okay, let us have the rules of logarithm. M, n, and b are positive real numbers and b is not equal to 1. We have the product rule. The logarithm of the product m times n to the base b is equal to logarithm of m to the base b plus logarithm of n to the base b. We have the quotient rule. Logarithm of m over n to the base b is equal to logarithm of m to the base b minus logarithm of n to the base b. Then we have power rule. We have logarithm of m raised to n to the base b is equal to n times the logarithm of m to the base b. Let's proceed to logarithmic equations. Here are some strategies for solving logarithmic equations. We can use the one-to-one property of logarithms, and also we can use rewriting to exponential form. Of course, the properties that we have just reviewed, the logarithmic properties. And then the zero factor property, that is if a, b is equal to 0, then a is equal to 0 or b equals 0 or both a and b are zeros. Let us have some examples. Find the value of x in the following equations. Number 1. The logarithm of 2x to the base 4 is equal to logarithm of 10 to the base 4. So we have two logarithmic expressions on the right hand side and the left hand sides of the equality with the same base, that is 4. We can rewrite this as 2x is equal to 10 using the one-to-one property of logarithms. So from here, divide both sides by 2, we have x equals 5. Checking our solution, substitute 5 to the x in the original equation. We have logarithm of 2 times 5 to the base 4 is equal to logarithm of 10 to the base 4. Logarithm of 10 to the base 4, because 2 times 5 is equal to 10. So the answer is correct. Example number 2, the logarithm of x squared minus 9 to the base 2 is equal to 4. So we only have a logarithmic expression on the left hand side of the equation, and on the right hand side we have 4. For our solution, we can rewrite this in its exponential form, that is x squared minus 9 equals 2 raised to 4. 2 raised to 4 is equal to 16, and then adding 9 to both sides of the equation, we get x squared equals 25. Then we have a quadratic equation. This type can be solved using extracting the square roots. So we have x equals positive negative 5. Let us check our answer. If x is equal to 5, let us substitute 5 to x in the original equation. We have logarithm of 5 squared minus 9 to the base 2 on the left hand side. Then we have logarithm of 25 minus 9 because 5 squared is 25. So we have logarithm of 16 to the base 2 is equal to 4. And 16 can be written as logarithm of 2 raised to 4 base 2 is equal to 4. Now in here, from the inverse property, the answer is correct. What if x is equal to negative 5? So we substitute negative 5 to x in the original equation. We have negative 5 squared minus 9. So 25 minus 9, and then logarithm of 16 to the base 2 equals 4. The same as in the previous checking. 16 is 2 raised to 4. So by inverse property, this answer is correct. Next example. The logarithm of x plus 1 to the base 2 plus logarithm of x minus 1 to the base 2 equals 3. So we have two logarithmic expression on the left hand side of the equality symbol. If this is the case, we can use the properties to write this as a single logarithm or a condensed logarithm. So for our solution, we will use the product rule. We have logarithm of x plus 1 times x minus 1 to the base 2 equals 3. And x plus 1 times x minus 1 is x squared minus 1. So from here, we can use the exponential form of this logarithmic equation. We have x squared minus 1 equals 2 raised to 3. And 2 raised to 3 is equal to 8. So add the negative of 8 to both sides of the equation. We have x squared minus 9 equals 0. Now x squared minus 9 can be factored as x plus 3 times x minus 3. So from here, we use the zero factor property. We can get the values of x as positive negative 3. Checking our solution, we will see that x equals 3 or positive 3 is the only solution because it is where logarithm of 3 plus 1 to the base 2 and logarithm of 3 minus 1 to the base 2 are defined. While for negative 3, the logarithm of negative 3 minus 1 yields a negative value for the argument, that's negative 2. And on the other expression, logarithm of negative 3 minus 1 to the base 2, again a negative value on the argument, that is negative 4. Hence, negative 3 is not a solution. Let's have example number 4. Logarithm x squared plus 2 logarithm of x minus 3 equals 0. Notice that the logarithmic expression here has no base written. If that's the case, this is understood to be under base 10. So let us have our solution. The equation can be factored as logarithm of x plus 3 times logarithm of x minus 1. So by zero factor property, we can equate each factor to 0. We have logarithm of x plus 3 equals 0. Subtract 3 from both sides. We have logarithm of x equals negative 3. Then we use the exponential form. So we have x is equal to 10 raised to negative 3. Then x is equal to 1 over 1000. The other factor, logarithm of x minus 1 equals 0. Add 1 to both sides. That's logarithm of x equals 1. Then, by exponential form, we have x is equal to 10 raised to 1 and x is equal to 10. Checking our solution, we will see that both 10 and 1 over 1000 are solutions, since if we substitute these to x in the original equation, logarithm of 10 and logarithm of 1 over 1000 are defined. Next, let us have example number 5. Use logarithms to solve for the value of x in the exponential equation. 2 raised to x is equal to 3. So notice that we have an exponential equation, 2 raised to x equals 3. By exponential equation, we can solve this by transforming each side of the equality into exponential expressions of the same base. However, 3 cannot be written as a power of 2. Hence, we're going to use logarithms to solve for x in this equation. By one-to-one property, we can write logarithm of 2 raised to x equals logarithm of 3. Using the power rule, we can get x logarithm of 2 in the left-hand side of the equation equals logarithm of 3. Then divide both sides by logarithm of 2. We have x equals logarithm of 3 over logarithm of 2. In our case, this is already the final answer because we're not allowed to use calculators. But if you're going to use your calculator, this will be approximately 1.58496. Okay, let us have property of logarithmic inequality. If b is between 0 and 1, then x sub 1 is less than x sub 2 if and only if the logarithm of x sub 1 to the base b is greater than logarithm of x sub 2 to the base b. Also, if b is greater than 1, then x sub 1 is less than x sub 2 if and only if the logarithm of x sub 1 to the base b is less than the logarithm of x sub 2 to the base b. We're going to use these properties in solving logarithmic inequalities. Let us have examples. Solve the following logarithmic inequalities. The logarithm of 2x minus 1 to the base 3 is greater than the logarithm of x plus 2 to the base 3. The first step in solving logarithmic inequalities is to ensure that the logarithmic expressions are defined. So for logarithm of 2x minus 1 to the base 3, x must be greater than 1/2. And in the right-hand side of the inequality, logarithm of x plus 2 to the base 3, x must be greater than negative 2. So this implies that for this inequality, x must be greater than 1/2. Since b is greater than 1, then we can write this as 2x minus 1 is greater than x plus 2. Adding negative x and also adding 1 to both sides of the inequality will get 2x minus x equals 2 plus 1. Simplifying, we have x is greater than 3. Hence, the solution set is the open interval 3 positive infinity. Next example, the logarithm of x is greater than negative 2 but less than 2. We can split this inequality into logarithm of x greater than negative 2 and logarithm of x is less than 2. Now, for logarithm of x is greater than negative 2, so we have logarithm of x is greater than logarithm of 10 raised to negative 2, that is by inverse property. Then, because the base is greater than 1, we can write this as x is greater than 10 raised to negative 2. And 10 raised to negative 2 is 1 over 100. Therefore, x is greater than 1 over 100. In the other inequality, we have the logarithm of x is less than the logarithm of 10 raised to 2. So 2 can be written as logarithm of 10 raised to 2 by inverse property. And then we have x is less than 10 raised to 2. And 10 raised to 2 is 100. Therefore, x is less than 100. Hence, our solution will be x is greater than 1 over 100 but less than 100. Next example, the logarithm of x to the base 1/5 is greater than negative 3. Let us have our solution. So we can write this as logarithm of x to the base 1/5 is greater than the logarithm of 1/5 raised to negative 3 to the base 1/5 by inverse property. Since the base is between 0 and 1, therefore we can write this as x is less than 1/5 raised to negative 3. And 1/5 raised to negative 3 is 5 cubed. Therefore, x is less than 125. Looking back at our logarithmic inequality, the logarithm of x to the base 1/5 is greater than negative 3. X cannot be 0 or a negative value. Therefore, our solution set will be all values of x greater than 0 but less than 125, or in interval notation we have 0, 125. Okay, let us have some practice exercises. In the practice exercises, you will be given 15 seconds to answer. You may pause the video if you need some more time to answer and then play again to check whether your answer is correct. Logarithm of 9x to the base 3 minus logarithm of x minus 8 to the base 3 equals 4. 15 seconds. Good. Time is up. Let us answer. So we can use the quotient property and write this as logarithm of 9x over x minus 8 to the base 3 equals 4. Then we can use the exponential form of this so that we have 9x over x minus 8 equals 3 raised to 4. And 3 raised to 4 is equal to 81. Multiply both sides by x minus 8. We'll get 9x equals 81 times the quantity x minus 8. Distributing 81 to x minus 8, we have 9x equals 81x minus 648. Then we have 648 equals 81x minus 9x. 81x minus 9x is 72x, and then divide both sides by 72. We get 648 over 72 equals x, and then 648 can be divided by 72. X equals 9. Next, The logarithm of 3x minus 5 to the base 8 is less than 2. 15 seconds. Okay, let us solve. Multiplying the right-hand side of the inequality by 1 in the form of logarithm of 8 base 8. We use base 8 because in the left-hand side we have the logarithm under base 8. Therefore, we will have logarithm of 3x minus 5 to the base 8 is less than the logarithm of 8 squared to the base 8 by power rule. And since the base is greater than 1, so we have 3x minus 5 is less than 8 squared. 8 squared is 64, then add 5 to both sides. We have 3x is less than 69. Divide both sides by 3, we have x is less than 23. Then our solution set will be all x greater than 5/3 but less than 23. X must be greater than 5/3 because in our inequality, x must be greater than 5/3 for it to be defined. Okay, that is all. For more exercises on this topic, you can download from the link given on the description of the video. Thank you for watching. Please subscribe for more math lessons.